Okay, so let's start. So today's topic will be about implementing a cryptographic algorithm, which you know as the present block cipher, and I will try to show you what you can do with the C language and what things you should be careful about. So as you know, the block size is 64 bits. So it is a good idea to store our variables in 64-bit registers. So for this reason, if you watch my ASCON video, I wrote something like this there. Okay. Oh, no, it wouldn't work like this, no. Okay, hold on a second. Yes. Okay, now I can write. Okay, so remember that I said type def unsigned to lower dash int 64, and I named this as bit 64 so that in the future I can just use bit 64. So this was just a type definition. After that, whenever you say bit 64, for instance a, this would give you a variable of 64 bits. But this is for actually Visual Studio. So this int64 representation is only valid for Visual Studio. So if you are using something else, you have to do something like type def unsigned long int bit 64. Okay, so just be careful about what kind of compiler you are using. This is important because this way you can generate 64-bit values, and unsigned means that the first bit of the our variable is also stored for values, but not for the sign. Normally, you know, plus or minus sign is represented with the first bit of the integer, but this way you keep it for our variables. So you can just simply say bit 64 state, so to keep the 64 bits of the input of present. Okay, so and another thing to watch out is that once you start working on 64-bit variables, in your implementations you might need smaller variables. Like for instance, you can define something like s here, an array value of s, which takes 16 possible inputs and 16 possible outputs. So this is an array of size 16, but the values are in 4 bits. So you can just store them in a byte. But we don't most of the time recommend that, because in the future, if you just perform operations between 8-bit values and 64-bit values, the compiler might act weird. So it is always a good idea to, you know, keep after this point on using 64-bit values. Okay, so this is how you define some stuff. Let me erase this too. Okay. Okay, so what we are going to do next. So let me stop this annotation. Okay, so let's look at the key schedule first instead of implementing the block cipher. First, I would recommend you to perform the write this key schedule and then use the test vectors here. Just take this key and check if all of these round keys works correctly. Okay, so here, as you can see, the first one starts with actually rotating 80-bit value 9 bits to the right. So here we actually encounter two problems. The first thing is that we don't have a register for 80 bits. The longest you can get is 64 bits. Actually, if you're using SSE instructions, you can have variables of 128 bits, but it would complicate things. So in your implementation, it is a good idea to use two variables, 64-bit variables for all your key. So most people just say bit 64, key low and key high. So this way, for instance, they keep the rightmost 64 bits in the key low and the remaining 16 bit at the key high. So maybe I should mention what does this look like. So assume that what you have is this. Okay. So okay, so this is not for drawing, I guess. Okay, so assume that you have just I cannot draw this. Okay, let me use this. Nope. Okay, so let's say that this is key low. Strange. Anyway, so you got another thing here. All of these are 64-bit values. So you just make them key low and key high. So keep the 64 bits at one side and 16 bits on the other side. But next thing we should do is actually to perform this rotation operation. And important thing is that we don't have an instruction for rotation. Okay, so but we have instruction for shifts. So let me give an example like this. So let me define like bit 64A equals to, for instance, all ones. So it will be 16 Fs. Okay, so this would give you 16 values of 64 bits of ones. So assume that we want to rotate it 3 bits to the left. Of course, if you rotate this, the result will be the same since all bits are 1, but I want to show you what happens when you shift something. So in our example, we want to perform 19 bits of rotation, right? So if you, for instance, say that we have temporary value as A, shifted right 19 bits. So this would actually shift the whole thing 19 bits to the right. So 19 ones here will be thrown out and there will be empty 19 bits at the beginning since you shift them to the right, and all of them will be initialized to 0. So this would give you 19 zeros, then remaining ones as 1. So next thing you need to do is as follows. You can perform the similar operation, temp2, let's say, and this time it is A shifted to, okay, let me do it like this, 64 minus 19 times to the left. Since you have shifted this many times to right, you have to shift it 64 minus 19 to the left. Since I put 64 here because we are dealing with 64-bit values. Okay, so final thing you need to do is to actually combine this, and you can do it like this. Okay, so you can say that now A equals to temp XOR temp2. So this would actually give you the rotation of A 19 bits to the right. Okay, so you can simply write a function to it, or you can just simply write it in a single line, something like this. So temp would be, for instance, A. If you want to rotate it L bits, okay, let me say it's T bits, it will be something like this. 64 minus T. Okay, so this will give you the rotation. So of course this is for a 64-bit value. Now you have to deal here with the 80-bit value, so you have to need to perform some tricks. Okay, so I'm not exactly solving this part, but I also want to show you something. Here you have a variable, but leftmost 4 bits are put inside an array value, array S. So now one thing you need to consider is how can I access 4 bits, leftmost 4 bits of a variable, right? So what you can do is as follows. So assume that I want to take the foremost leftmost bits. So what you can do is as follows. So if I want to access to 4 bits, leftmost 4 bits of A, I can just say that temp is equals to A shifted 60 bits. So this will be enough because I told you that when you shift it, the remaining parts are initialized to 0. But if you want to access something 4 bits in the middle, for instance, if you want to shift it to the right 10 bits but only want to focus on the rightmost 4 bits, what you need to do is to end this thing with 0xf, so that for instance in this case A had a 64-bit value. Once you shifted 10 bits to the right, now it is 54 bits, but once you end it with 4 bits of ones, you just access to the rightmost 4 bits. Now you can put it inside this array and take the output value and write it here. Okay, so these are some of the things you need to focus. And let's say that this is done. You somehow managed to implement the key schedule. Then what we do is, now that we have the key schedule, we want to implement the algorithm itself, right? So now you can take all of the 4-bit values, put it inside the S box, write the output here, then perform the permutation operation. So in this case, you have to access every single bit and move them to some places. So you can do it in a for loop of 64 bits. You can write a function which actually looks at the permutation array and as an input takes the input value of the place and just moves it to the output place. So in this case it is 0 to 0, 1 to 16 and so on. So this is actually the naive way of implementing an algorithm. So you just simply implement every step one by one, right? But of course this is not the only way of implementing it. So in your homework I'm expecting you to do this, but in crypto we need performance, and this would not give you much performance because this algorithm is a hardware oriented algorithm. We have a lot of bit operations, so performing this many bit operations will actually slow down your implementation on CPU. So what you can do is to change your implementation technique. So now I'm going to talk a second implementation technique. So we can say that the first one is the naive approach or the direct approach, but the second one is called table-based implementation. So in this case, you make the following observation. So let's focus on the parts of the cipher in terms of S boxes. So this S box can have 16 different values, right? After the key XOR, the possible inputs to this S box can be 0, 1 to F, right? There can be 16 different values. And the output will be 16 different values again, depending on this S box. Then all of these 4 bits are scattered around and you know which places it's going. So instead of doing this operation in every round and so on, you can say that, okay, let me pre-compute all of the possible inputs here, which are 16, and let me compute all of the possible outputs. You also know, of course, the possible outputs of the S-box, but you also perform the linear layer, and you just scatter these bits to the places they need to go and store them in a 64-bit value here, right? So you can create a table, say that this is table 0. It is an array of size 16, so it takes 16 possible inputs, but the outputs are 64-bit values. So you can do the same thing for S1, S2, and S3, so you can generate 16 tables for all of these parts. So this way, the implementation turns into this. Instead of performing the encryption, a single run after the key XOR, or if you put the key XOR later. So for instance, let's say that state is the input 64 bits. So your actually one round of implementation turns into this. So T0 is the table you generated for this S0. As an input to this array, you put state, but only the rightmost 4 bits of the state. Then you XOR it with the output of the first table, which is the input of S1. So this time it is T1, but state shifted to right 4 bits, and then you end it with again 0xf. Then you combine it with T2, which is again state, but this time shifted to 8 bits, and end with 0xf. I think you get the picture. You keep doing this until you get T15. This time state is shifted to 60 bits. There is no need to end it with 0xf because it is only 64 bits. So this is actually the output here. All of these XORs give you here. So if you have the following round key, let's say that it is RK1. This is just one round of encryption. So as you can see, instead of performing 16 S-box operations and performing 64-bit bit replacements, we turned it into 16 table lookups. You are just looking at the value of the array here, and you XOR all of them. You also XOR the round key at the end, so that this turns into 16 XOR operations and 16 table lookups. But of course, there are also logical operations we perform here, shifts and ends. But as you can see, this is a single round of present. So if you achieve this, if you create these tables, now your implementation will be something like just a for loop, which is for 31 rounds, that runs this single line of code. Okay, as simple as that. Of course, here instead of RK1, we can say RKI as the ith round key, and you can write a for loop in terms of I. So as you can see, we have a very different approach here, and we don't perform bit operations. We just perform table lookups and XORs and shifts. So this way it is really fast on CPUs compared to the naive approach. So if you don't have any questions, I will continue to the third approach, which would be somewhat different than this. Okay, I will try to draw, but it doesn't work as I expect it to be. Let me check. Okay, what I was trying to show you is this. So assume that I have a 64-bit value, right? Like this. This is just 64 bits, okay? Okay. Strange, it doesn't allow me to draw on top of it. Okay. I have to come up with something else. Okay. Let's say that this is our 64-bit value. So all of the bits are kept here. Anyway, okay, so what I was trying to show you is something like this. I will just use the text value instead. So once you create a 64-bit value, so let's represent all of the bits with this, okay? A2, let me start with this one. I expected the draw function was better, but it turned out to be really bad. So these are the, once you create a 64-bit value, assume that all these are the 64 bits that we were dealing so far. So we were trying to access these bits, you know, change their positions, rotate them, and so on. So you just simply create a 64-bit value, but accessing them becomes really hard. So instead of doing this, idea is as follows. Instead of generating a single variable, just generate 64-bit different values like B64. Okay, so and our aim is to keep every single bit in this array. Okay, so instead of thinking horizontally, now you have to think vertically. Okay, so now if you go back to our picture and assume that we want to change the positions of the bits, third bit and the 60th bit, let's say. So this just becomes, you know, temp equals to, let's say we want to replace the third bit with the 60th bit. So this is just what happens. The classical swap operation where you use a temporary value to obtain. Okay, so as you can see, now instead of trying to shifting, ending, and obtaining the value, we already keep all of the bits in a single array, so we can simply work on the bits. So you might think that, but this is a waste of space, because for a single bit, I'm keeping a 64-bit array. So good thing is that since this is a 64-bit array, so you don't need to keep a single bit at B3, but you can keep 64 different values. So assume that you want to encrypt 64 blocks. You can just keep all of the 64 blocks in here. Okay, so once you perform this operation, you are not simply shifting the bits on a single block, you are performing the same operation for 64 different blocks. Okay, so this is called bit slice technique. You are actually slicing the bits and performing operations on bits. So this way you actually provide a SIMP level parallelism at the software level. SIMP means that single instruction, multiple data. With a single instruction here, you're actually swapping bits of 64 different blocks. Okay, so these three approaches might be very useful when you are performing encryption. So again, in the homework, you are not expected to perform table-based implementation or a bit-sliced implementation, but you have to keep in mind that there are other implementation techniques which can provide a very fast implementation. For instance, in the previous one, I told you to keep a table for 16 S boxes, but you can actually double your performance by doing this. Since this is just, if you just combine these two S boxes, this is just 8-bit input and 8-bit output. So now it becomes an array of size 256, which is very small, that you can keep in the memory. So now instead of generating 16 tables, you just combine two consecutive S boxes, so that you just simply generate 8 tables. So in our previous example, I showed you how to implement a single round by performing 16 table lookups and 16 XORs. Now it turned into 8 table lookups and 8 XORs.